everyone. My name is Dr. Nandit and I am working as Assistant Professor at AKGEC, Ghaziabad. So today I'll be covering the topic Relations and Types of Relations, which is a topic from Discrete Structures and Theory of Logic. The topics which I'll be covering in order to understand what exactly is a relation and what are the types of relation include ordered pair, Cartesian product, properties of Cartesian product which can be applied directly. Then what do we mean by relations? Then we'll be covering a few examples on relations and types of relations. To start, first of all, let's discuss that what is an ordered pair. When I talk about ordered pair, it is something without which I cannot understand relations. So, what exactly is an ordered pair? As the name says, ordered and pair. So, it is going to have pairs of objects in which the order of the components or objects is important. So, an ordered pair can be thought of as a pair of objects where the components occur in a specified order or a spatial order. It can be written by listing down the components from both the pairs of sets in such that they are separated by commas and enclosed within parentheses. So, if I talk about XY ordered pair, it actually represents an ordered pair where the first component X has been taken from a set, say A, and the other component has been taken from another set B. And here the order of these two objects is important. That is, X will, the first component is going to be from the first set and the second component has to be from the second set. So that is why we are emphasizing on the point that the order of these objects is going to be restricted. We cannot change the order of these objects. Now, when I come to the Cartesian product, now what exactly is a Cartesian product? If I have any two sets A and B, then the Cartesian product of these sets is denoted by A cross B. And what it is going to contain? It is going to contain the components A comma B, where the object A will belong to the set capital A and small b is an object which belongs to the set capital B. So here it is going to contain all the elements where the first component comes from set A and the second component comes from set B. Let's take an example. Suppose I have a set A which contains the elements 1, 2 and I have another set B which contains the elements small a, small b. Now I want to find out the Cartesian product, that is A cross B. So now my A cross B will contain all the elements such that the first component should belong to set A and the second component should belong to set B. So all the components which are possible with this property include 1, A. Here 1 belongs to set A and A belongs to set B. Then I'll have another component 1, B. Then 2, A and 2, B. So this is the set of all the possible combinations such that the first object should belong to set A and the second should belong to B. So this is my Cartesian product A cross B for this A and B. Now we have various properties of Cartesian product which are followed by all the sets. Now suppose I have 4 sets A, B, C and D. So if I take the intersection of AB and intersection of CD and then I take the Cartesian product of these two resultant sets. So this will be same or equivalent as the Cartesian product of A and C, Cartesian product of B and D, and then I take the intersection. So I can apply this property of Cartesian product to sets directly. The second property says that if I have 3 sets A, B and C and I find out the set difference A minus B and then I take its Cartesian product with the third set C. This is same as A Cartesian product C, B Cartesian product C and then the set difference. So the LHS will be equivalent to RHS. The third property says that again if I have 3 sets A, B and C and I take the union of A and B, and then I take out its Cartesian product with the third set C. So this will be same as A Cartesian product C, B Cartesian product C, and then when I take its union. So the LHS will be equivalent to RHS. Here again, this is a property which could be directly applied for Cartesian product. The fourth property says that I have three sets A, B and C. I take the intersection of BC and then the result, with this result I take the Cartesian product of with A. So this will be same as A Cartesian product B, A Cartesian product C, and then the intersection. So here again the LHS will be equivalent to the RHS. So these are the four major properties of Cartesian product which can be applied whenever we are making use of Cartesian product on sets. So now coming to relations. As we have already seen that what is my ordered pair and what is the Cartesian product, now we'll come to what exactly is a relation. So a relation is nothing. If I try to define it, it is going to be a subset of the Cartesian product. So first we'll see that if I have two sets A and B and I have a binary relation from set A to set B, then the relation is nothing but a subset of the Cartesian product A cross B. Here we have denoted the same thing with the help of symbols, that is R is a subset of A cross B, means R is a set of all the ordered pairs of the form A comma B, where A belongs to the set capital A and small b belongs to the set capital B. Now we use the notation ARB to say that the ordered pair A comma B belongs to the relation R. So this is the standard notation which we use in order to explain that A comma B belongs to the relation. And if A comma B is a ordered pair which does not belong to the relation, then we use the notation A R not B. This denotes that A comma B is a ordered pair which doesn't belong to the relation R. So if we have ARB, we say that A is related to B by relation R. Now let's take an example. Suppose I have a set A which contains three elements, that is A, B and C, and I have a set B which contains three elements 1, 2 and 3. Now I have the first part, that is R, which contains A comma 1, B comma 2 and C comma 2 is a relation from A to B. Now if I check this relation, I can clearly see that the first component of each of the element belongs to the set A and the second component belongs to the set B. So it is clear from this that R denotes a relation from A to B. So the answer is yes. Now let's check for the relation Q. Q contains 1 comma A, 2 comma B. Is it a relation from A to B? Now if I check the first component for each element, it belongs to set B and the second component belongs to set A. So I cannot say that it is a relation from set A to B. So it is not a relation from set A to B. So we have written the answer as no. Now coming to the third relation, that is P, which contains the elements A comma A, B comma C and B comma A. Is it a relation from A to A? So yes, if I see A contains the elements A comma B comma C. So in P, both the components are from set A for every element. A comma A, then B comma C both belong to A, then B comma A also belong to A. So I can say that it is a relation from A to A. So the answer is going to be yes. So this is the definition of relation and this is how we identify that whether a given ordered pair of elements is in relation or not. Now talking about the domain of a relation and range of a relation. When I say that my relation is a subset of Cartesian product, so I know that it is going to contain the pairs of elements where the first component is going to belong to some set A and the second component is going to belong to some set B. Okay, so if I talk about the domain of a relation, it is a set which will contain all the elements of the ordered pair which belong to the first set, or the first elements of all the ordered pairs is going to form a domain of the relation. And if I talk about the range of the relation, then the second component of all the elements is going to form the range of the relation. Let's see this with the help of an example. If I have two sets x and y, where my x contains 5 elements 1, 2, 3, 4 and 5, and the second set y contains 3 elements, that is 4, 5 and 6. Now here the relation R is defined from x to y. And what does the definition of this relation says? It says that R is going to contain all the x comma y pair, where small x is going to belong to capital X and small y will belong to set capital Y. But the condition is if the value of x is going to be greater than y. So now if I check my sets and I try to find out the ordered pairs which are going to belong to the relation, then I can put only those ordered pairs where the first component is going to be less than the greater than the second component. So I am going to get only one ordered pair over here, that is 5, 4, where 5 belongs to x and this 4 belongs to y. If I take any other element, it is not going to fulfill the condition of x greater than y. So there is only one element in this relation, that is 5, 4. So now if I want to find out that what is the domain for this relation is going to be 5 and the range is going to be 4. So this is how I define the domain and range of a relation. Now this is again another example where we are saying that a relation on only a single set. Till now I was talking about that I am having a set of ordered pairs in my relation where the first component is going to belong to some set A and the second component is going to belong to some other set B. But now I'll be talking about a relation where I have only a single set A and both the components will belong to the set A only. So a relation on a set A is a relation from A to itself. Now let's take the example. Suppose I have a set A which contains 4 elements 1, 2, 3, 4, and the relation RDEF is defined as it will contain the ordered pairs A, B such that A should divide B. Now what this relation RDEF will contain? Let's see. Now this relation is on set A, from set A to A. So that means the other component will also, second component will also belong to set A itself. Now if I talk about 1, this 1 is going to divide every element. So 1 divides 2, 1 divides 3, 1 divides 4, even 1 divides 1. So all these pairs will be there in this set, in this relation, that is 1, 1, 1, 2, then I have 1, 3 and 1, 4. What other things we can have? If I talk about 2, 2 is not going to divide 3, but 2 is going to divide 4. So I'll even have 2, 4 in this relation. Other than this, I'm not going to have any other elements. So this is going to be my RDEF. So this is how I define a relation R from a set A to itself. Now, when I look at this, that is, I am talking about relations from set A to itself, then one thing which we must know that how many total relations are possible on a set A with cardinality n. So that means how many relations are possible if my set A contains n elements. Now let's see how to solve this. Now set A has n elements, that is I can write set A as 1, 2, 3 up to n because it is containing n elements. Now if I talk about its Cartesian product, that is A cross A, because here we are talking about a relation from set A to itself. So it will contain n square elements because I have A with n elements. Here also I have n elements, here also I have n elements. So whenever I calculate A cross A, it will contain a total of n square elements. Now, from my definition only, I am saying that what is a relation? A relation is a subset of the Cartesian product. So, now if I talk about how many subsets are possible for a Cartesian product with n square elements. So, I know that if I want to calculate the number of subsets for a set containing L elements, the general formula is 2 to the power n. Now, the number of elements which I have, in place of n, I have n square elements. So, how many subsets are possible? 2 to the power n square. So, this is the total possible number of relations for a set A which will be containing n elements. Now, the same thing that we have calculated just now, there is an example for it. Suppose my set A contains 2 elements, 1, 2. So, now if I try to calculate its Cartesian product will contain all the ordered pairs which are possible from set A to set A. So, it will be containing 1, 1, then 1, 2, 2, 1 and 2, 2. This is my A cross A. Now, if I want to find out the number of possible relations, or we can say subsets of A cross A, so phi is always a subset of every set. So, I'll have phi, then I'll take all the single elements, that is 1, 1 is possible, that my relation can have only 1, 1, or it might have only 1, 2, 2, 1, 2, 2. So, again 4 subsets are possible with combination of elements where I have single elements. Now, if I take the combination of two elements at a time, then how many total combinations are possible? I can have 1, 1, 1, 2, or I can have 1, 1, 2, 1. Same way 1, 1, 2, 2, or I may have 1, 2, 2, 1, or I might have 1, 2, 2, 2, or the last one, that is 2, 1 or 2, 2. So, total number of relations possible this way can be 6. Now, I can even have the combination of 3 elements. So, with 3 elements, the possible combination is 4 subsets. So, I can have 4 subsets with combination of elements in a group of 3. Now, I might take the entire A cross A as my subset. So, that is 1. Now, if I sum up all these, I get a total as 16. That is 16 relations are possible when my set A contains 2 elements. Now, if I substitute this in the standard formula, which we had discussed right away, that is 2 to the power n square. Now, the value of n is 2. So, 2 to the power 4, which is nothing but 16. So, this is to show that we can calculate the number of possible relations by using this formula, or we can even check it using by listing all the relations which are possible. Now, coming to the types of relations. We can have identity relation, we can have inverse relation, we can have reflexive relations, symmetric relations, or transitive relations. So, first we'll talk about the identity relation. An identity relation is a relation which contains only A, A pairs. For example, I have a set A which contains 2 elements, that is 1, 2. Now, what is going to be the identity relation for this set A? Now, my identity relation IA will contain only the pairs of elements which will be in the form of A, A. So, for this set A, I can have 1, 1 or 2, 2. These are the 2 A, A pairs which can be possible for this set A. So, my identity relation is going to contain 1, 1 and 2, 2. So, this is the identity relation. Same way, if I have a set A with 3 elements A, B and C, so my IA is going to contain all the diagonal elements, that is A, B, B and C, C. So, an identity relation is going to contain all the diagonal elements only. Now, coming to the next relation, that is the inverse relation. If I talk about the inverse relation, right now we were talking that if I have a relation R, it is actually going to contain a ordered pair A, B. Okay. So now if I talk about its inverse, its inverse is nothing but R inverse will contain the ordered pair in the reverse order, that is B comma A. So this is what a inverse relation is. So a inverse relation is seen when a set has elements which are inverse pairs of another set. So for example, if I have a relation A comma relation containing the elements A comma B and C comma D, then its inverse will contain B comma A and D comma C. So this is the inverse. This is the standard definition of a inverse relation, that is, it will contain, a inverse relation will contain the ordered pairs B comma A such that the ordered pair A comma B should be in R. Now let's talk about a reflexive relation. So a reflexive relation is any relation which always has the diagonal elements, and other than diagonal elements it can have anything. But the only necessary condition for a relation to be reflexive is that it should have the diagonal elements or the elements which are of the form A comma A. So let's take the example of a set A which contains two elements 1 comma 2. Now if I talk about a relation which has to be reflexive, there will be two diagonal elements for this particular relation, that is 1 comma 1 and 2 comma 2. So any relation which will be reflexive for this set A, it should minimum have these two elements. Other than these two elements, it can have any element or it might not have any element, but it is going to be reflexive. So the only necessary condition for a relation to be reflexive is that it should contain the diagonal elements. So now if I look at this relation R, where I have 1 comma 1 and 2 comma 2 pair along with 1 comma 2 and 2 comma 1, yes, it is a reflexive relation because it is having these two diagonal elements. So now if I try to find out the cardinality of smallest and largest reflexive relation, since I know that for my relation to be reflexive, the only condition is it should have the diagonal elements. So if my set A has n elements 1 comma 2 up to n. Now how many diagonal elements this relation is going to have? It will be having n diagonal elements. How? All the ordered pairs, that is 1 comma 1, 2 comma 2 up to n comma n. All these elements should be there. So I'll have n diagonal elements. So my smallest reflexive relation will minimum have these n elements. So the cardinality of smallest reflexive relation is R. And if I talk about the cardinality of largest reflexive relation, so obviously if I try to take out A cross A, it will contain all the diagonal elements as well as all other possible elements. So the cardinality of this A cross A is n square. So I can say that my largest reflexive relation will contain n square elements. So this is the cardinality of largest reflexive relation. Now let's talk about that how many reflexive relations are possible for a set with cardinality n. So in order to understand this, first we'll try to focus on a set which contains only two elements. So for two elements, we'll try to check out how many reflexive relations are possible. So if I talk about this set A which contains two elements, that is 1 comma 2. So for this relation to be reflexive, it must contain minimum two elements, that is 1 comma 1 and 2 comma 2. So how many relations can be there? The smallest relation, that is, it will be having 1 comma 1 and 2 comma 2. Now it may contain the other elements, that is, it might have 1 comma 2 pair, it might have 2 comma 1 pair, or it might have all the elements, that is A cross A. 1 comma 1, 2 comma 2 are there, then it has 1 comma 2 and 2 comma 1. So if my A was having two elements, so the number of possible reflexive relations came out to be 4. I can see these relations, and these are the only possible relations which will be reflexive for the set A with two elements. Now we'll be talking about a set A which will contain n elements. So how many reflexive relations are possible? Let's try to solve this. So if I have a set A with n elements, that is 1 comma 2 up to n, then my A cross A will contain 1 comma 1, 1 comma 2 and this way up to n comma n. Now what I try to do, I first try to divide this entire thing into two parts. One, I'll have all the diagonal elements and then I'll have the remaining elements. Now see, what is going to be the cardinality of A cross A, or how many elements in total are there? There are total of n square elements if I talk about the total elements, because A cross A contains n square elements. Now if I talk about the diagonal elements, how many diagonal elements I have? I have n diagonal elements. And how many elements will be remaining if I remove the diagonal elements? Since I have total elements as n square and diagonal elements as n, so it becomes n square minus n. So these are my remaining elements. Now, if I look at these diagonal elements, how many choices I have for these diagonal elements? I have only a single choice, that is, I'll have to include it in my relation in order to have a reflexive relation. So anyways, I have only one choice for all these diagonal elements, that is to include them. Now, if I talk about the remaining elements, that is n square minus n elements, how many choices I have for these? I have two choices. I may include them or I may not include them, but it is not going to affect the reflexive nature of my relation. So, since I have two choices only for these non-diagonal elements, the number of reflexive relations which is going to be possible is 2 to the power n square minus n. So, this is the total number of reflexive relations which are possible if I have a set A with cardinality n. Now, let's talk about that. What is a symmetric relation? So, a symmetric relation means that if in my relation I have a A comma B pair where the values of A and B are different, then in that case I must have B comma A pair in order to make that relation symmetric. So, if I go by the definition, in a symmetric relation, if A is equal to B is true, then B will be equal to A will also be true. So, for diagonal elements, if I have my only diagonal elements, the relation is symmetric. Okay. But if I am talking about some elements where A and B are not equal, then a symmetric relation will only have B comma A pair which will belong to the relation R. It should be true whenever I have a comma B element in my relation. An example of a symmetric relation, we can see that if my relation R has this pair 1 comma 2 and it also has another pair 2 comma 1. So what can I say? I can say that this relation is symmetric for a set A which contains two elements 1 comma 2. Now let's find out the cardinality of smallest and largest symmetric relation. Now suppose there is no element in my relation. So by default it is symmetric, because if I have a comma B pair, then only I will be looking for a B comma A pair. So if I talk about the cardinality of smallest symmetric relation, it is going to be 0, because my relation with no element, it is by default symmetric. Okay, and what is going to be the cardinality of largest reflexive relation? A cross A. My A cross A will contain all the elements. So for every A comma B pair, it will always have B comma A pair. So I can say that the cardinality of largest symmetric relation is going to be n square. Now, if we want to see that how many symmetric relations are possible for a set A with cardinality n. So, to understand that, let's again take an example of set A with only two elements, that is 1 comma 2. So, for this relation to be reflexive, it must contain a B comma A pair if there is a comma B pair. So, all the possible symmetric relations have been listed down. So, relation 1, R1, if it has no elements, it is symmetric. If it has 1 comma 1, it is again symmetric. If it has 2 comma 2, it is again symmetric. If it has both the diagonal pairs, that is 1 comma 1 and 2 comma 2, it is also symmetric. Now, R5, we have this one diagonal element and we have the pair 1 comma 2 and 2 comma 1, because if I leave any of these elements and take only one, then my relation will not remain symmetric. So, I need to have this pair. So, it is again symmetric. R6, I have one diagonal element and along with that diagonal element, I have this pair. Then R7, I have only the pair 1 comma 2 and 2 comma 1. And for my R8, I have the diagonal elements along with the pair. So, that is nothing but A cross A. So, in total, I have these 8 relations which are symmetric, which are possible for this set A, which contains only 2 elements. So now let's see that if my set A has the cardinality n or contains n elements, so how many symmetric relations are possible. So now my set A has n elements 1, 2 up to n. So if I calculate its A cross A, it is going to be 1, 1, 1, 2. It will contain all the elements up to n, n. Again, I can divide my A cross A into 2 parts. One which is having the diagonal element part, and the other one is the remaining elements part. So all these are my diagonal elements which are possible, and the remaining elements will always be of the form like 1, 2, 2, 1. Then I can have 1, 3, 3, 1, and so on up till 1, n, 1, and it will go on like this. Now, if I see the diagonal elements, how many diagonal elements I have? N. And the remaining elements are n square minus n, because the total number of elements in A cross A were n square. So the remaining elements become n square minus n. Now if I look at these diagonal elements, how many choices I have for these diagonal elements? I have 2 choices, because I may include these diagonal elements or I may not include these diagonal elements. It is not going to affect the symmetric nature of my relation. So I have 2 choices for all the diagonal elements. So the possibility for the relations using these diagonal elements is 2 to the power n. Now let's see for the remaining elements. Now I have remaining elements as n square minus n. But the only thing is that these elements can only exist in pairs. It cannot happen that 1, 2 is there in the relation and 2, 1 is not there, because then the relation will not remain symmetric. So they have to occur in pairs. So if I talk about pairs, how many pairs I have in total? N square minus n by 2. So these are the total number of pairs which will be possible with these elements. And for each pair, how many choices I have? For each pair, I have 2 choices. Either I can include that pair or I may not include that pair. So I have 2 choices for every pair. That means 2 to the power n square minus n by 2. So this is going to be the total number of symmetric relations which will be possible for a set A which will contain n elements. Now coming to the transitive relation, a relation is said to be transitive if I have 2 pairs, that is A, B and B, C in my relation. Then I must have the A, C pair also in my relation for a relation to be transitive. Let's take an example. If I have a relation R, I am defining this relation on set A only, okay. I have these 3 elements and the relation is defined on the set A only. Then I have an element 1, 3 and 3, 2. So now in this case, I have A, B, B, C. So to make this relation transitive, I must have 1, 2 also in this relation. Then it will become transitive. So if I talk about the cardinality of smallest and largest transitive relation, so if it doesn't contain anything by default, it is going to be transitive. So cardinality of smallest relation which is transitive is going to be 0. And if I take the entire A cross A whose cardinality is going to be n square, so that is going to be my largest transitive relation which will be possible. So that's all for this lecture. Thank you.